All right, now that Chemistry Organic 2330, we're going to continue on with Chapter 16, Organic Polymer Chemistry, with a particular type of chemistry, which we call step growth polymerization. We learned a little bit about what polymers are, the fact that they're very large molecules, and the fact that they have different morphologies, but they can also have different chemistries. So in a step growth polymerization, it's a type of polymerization where we typically grow the chain by adding one kind of functionality to another kind of functionality, and then the A functionality with the B functionality, A, B, A, B, A, B. And we alternate the different functional groups, okay? These are very common in what we call tough polymers like polyamides, polyesters, polycarbonates, polyurethanes, and epoxies. Okay, each of these has two functional groups joining together to create the polymer functional group that we're going to be using. Okay, so the first one we're going to talk about are called polyamides, and the first one we'll talk about is what we call nylon 6,6. In nylon 6,6, we take a 6-carbon carboxylic acid chain and we react it with a 6-carbon diamine, and that creates our polymer that has 6 carboxylic acid carbons plus 6 amine carbons, and it alternates back and forth, back and forth, back and forth. So the way we do that is we take this dicarboxylic acid that we have right here. It's also known as a diptic acid. Okay, notice there's a total of 1, 2, 3, 4, 5, 6 carbons, including the carbonyl carbons. And we have this thing called 1,6-hexane diamine. So we have 2 amines, 1 at each end, plus 1, 2, 3, 4, 5, 6 carbons in there. So that's where we get the 6 and the 6 in nylon 6,6. This is typically made by just reacting the carboxylic acid with the amine. When they do it, that's an acid-base reaction. They don't form a new bond, but they do form an ionic bond between them. And this is what we call the nylon salt. Okay, so this just creates a salt of the carboxylic acid and amine, and then we have to heat it up under pressure to remove water. And when we remove that water, it's typically called a condensation, or we remove water from the system, giving us our polymer. Okay, so our new bond that we've created here is our new amide bond. So our carboxylic acid plus amine creates our amide bond, hence the name polyamide. Okay. When we make these polymers, they tend to start out as fairly low crystalline materials, but the fact that the amide functionality can hydrogen bond means that if we take these fibers and pull them out such that the chains start to align and we can align the hydrogen bonding amine hydrogen with the hydrogen bondable carbonyl oxygen, we can end up with this very strong, very crystalline material. And that's what gives nylon fibers their very high strength, is that they are pulled out, aligned and crystalline, and they also have that hydrogen bond, which is a very strong bond. Okay, so how do we make nylon 6,6? It turns out we actually take benzene itself, we catalyze it down to cyclohexane and then oxidize it to get our cyclohexanol. Once we get to cyclohexanol, we can actually clip the chain open right here next to this alcohol and get our 6-carbon carboxylic acid, or a diptic acid. Okay. So this is actually a derivative of a petrochemical product. They get the benzene from petrochemical sources. Okay. Now, interestingly enough, what we do is we do a rearrangement reaction to make the diamine compound. So we take the adiptic acid and make it the ammonium salt. And so we have this ammonia adiptate right here. And then by heating it, we get to this diamide structure. And once we have that diamide structure, we can hydrogenate the carbonyl compounds off here. When we hydrogenate the carbonyl compounds on here, those carbonyl carbons turn into the last 2 methylenes here, and we have 6 carbons in there. So we're using benzene to create not only the dicarboxylic acid functionality, but we're taking that dicarboxylic acid and turning it into our diamine. So both parts of the nylon 6,6 are made from benzene. Okay. In addition to nylon 6,6, we have what we call nylon 6. In the case of nylon 6, we actually have a ring opening polymerization. So remember when we talked about amides, we had the possibility of forming cyclic amides, and those cyclic amides are called lactams, okay? This particular one is called caprolactam because it has a total of 5 methylenes between the nitrogen and the carbonyl carbon, okay? So when we take this and partially ring open it up such that the cyclic amide turns into a linear amide, we now have nylon 6 because there's a total of 6 carbons in between each of the nitrogens. So we go from nylon 6,6, which is done with a dicarboxylic acid and a diamine, to nylon 6, which is the ring opening of a cyclic amide. Now these form not as much hydrogen bonding as the nylon 6,6, but they're still very useful. They can be drawn out into fibers and still do some hydrogen bonding. Okay, a polyamide derivative here. The 2 previous ones we did with, we had flexible aliphatic chains, and that made them be able to draw out and be very strong fibers. However, if you replace that 6-membered long chain with a benzene ring, we have what we call an aromatic polyamide or an aramid, okay? The most common of these is Kevlar. In Kevlar, we take a 1,4-dicarboxylic acid of benzene, and we react it with a 1,4-diamino benzene, and we get this very rigid structure of benzene, amide, benzene, amide, benzene. Okay. Now, because it's so rigid in between the different functional groups, and those functional groups can hydrogen bond, they become very strong when they're drawn out as fibers. In fact, they're used in bulletproof vests, bulletproof jackets, fire-resistant raincoats. And there's another derivative that has the meta derivative that's also used in Nomex, which is another fire-resistant polyamide fiber. Okay, moving from polyamides to polyesters. So in polyesters, we just have that ester functionality. So we take a carboxylic acid and react it with an alcohol to give us our ester. Now, industrially, most of the times what we do is we do a transesterification. Just like we did a transesterification in our esters chapter, we take a salt of, in this case, terephthalic acid, or the 1,4-benzene carboxylic acid, and we make it into the diethyl ester. And then we react it with a higher boiling alcohol, in this case, ethylene glycol, or 1,2-ethane diol, and it gives off methanol as it goes, because methanol boils at 50 degrees, and we end up with our polymer right here. Now, again, this is PET, or polyethylene terephthalate, and we can use it as a fiber, a film, or a molding bottle. Okay. So how do we make these industrially? Well, we start with petrochemical derivatives, of course. We start with ethylene gas, and we oxidize that with oxygen to give us ethylene oxide, and then we react that with water to give us our 1,2-ethane diol, which is also known by its common name as ethylene glycol. We can also take the terephthalic acid that we used for the aramids. We make that industrially as well by taking a petrochemical derivative of benzene, which we call xylene. It has a methyl group on each side here, and we oxidize those down to carboxylic acids using a catalyst, and that's how we end up making the terephthalic acid for both the PET as well as the Kevlar. Okay. Similar to polyesters is a thing called polycarbonates. In the case of a polycarbonate, what you have is a single carbonyl with 2 oxygen bonds onto it. So instead of making it by taking an ester and transesterifying it, what they do is they take a diacid chloride of just a carbonyl compound here, and they react it with a salt of an alcohol. In this case, we use what we call bisphenol A. Okay, so in bisphenol A, we have 2 phenols hooked onto this dimethyl group here, and it reacts with the phosgene to give us sodium chloride as well as our polymer. Okay, this is a polycarbonate. It's more commonly known as lexan. It's what a lot of safety glasses are made of, as well as polymer lenses for your eyeglasses are also made out of lexan. Okay, so the great thing about lexan is because it has that aromatic unit, and because it has a very small the chain in between that carbonate unit in between the two aromatic rings, it makes it a very tough material. It has a very high impact and tensile strength, which means it's tough when you hit it, but it's also tough when you pull on it. And it keeps that range all the way from probably a very low temperature, so it can be used in snowmobiles and snowmobile helmets, to a very high temperature right before it melts. It keeps its manufacture, it keeps its strength. And so it's used for making break resistant windows, bullet resistant glass, etc. Okay. So another step growth polymerization we have is what we call a polyurethane. In the case of polyurethane, what we have is it's an ester on one side and an amide on the other side. And we typically make this by taking what we call an isocyanate. So it's this nitrogen, carbon, oxygen structure here, and we react it with an alcohol to create the amide on this side and the ester on this side. So that is chemically known as a carbamate, but industrially it's known as a urethane. So in this case, we can make a wide range of polyurethanes by taking an isocyanate and reacting with an alcohol. Note, this does make nice fibers, but it's also used industrially to make foams. So when you hear a polyurethane foams, they can be flexible or rigid, and they're typically made by using an isocyanate with an alcohol. Okay. So when we make fibers out of this, one of the common things we use is what we call this 2,6-toluene diisocyanate. So this is our toluene functionality here. And then we have two isocyanates on it, and then we react it with some kind of polymer that has two OHs on it, two alcohols on it. And then what that does is that creates this soft section, is the thing in between the two alcohols. And then that rigid section is where the toluene diisocyanate was. And so we end up with this soft, elastic, stretchy material. And when we turn it into fibers, it's also known as spandex or lycra. Okay, the last of those step growth polymer systems I want to talk about are called epoxy resins. Okay, so in the ether chapter, we learned that we can have a three-membered ether ring that is called an epoxy. So what we can do is we can take those epoxies and open them up and make them polymerize. Typically, when we have an epoxy reaction, we have more than two epoxies, and we typically react it with something like an amine to polymerize it. Okay, so how do we make that? Well, just like with the polycarbonate, we start with a compound known as bisphenol A, and again, we turn it into the salt here, and we can react the O negative charge here as a nucleophile onto a chloro epoxy compound called epichlorohydrin, and that'll generate our di-epoxy compound. So this tends to be what is used in like an epoxy resin. So if you have a tube of epoxy, one side is kind of clear and kind of viscous, the other side has a slight yellow tint and smells really bad. Okay, this di-epoxy is typically the clear one that has the higher viscosity. Okay, so in that other tube, the yellowish one that looks bad, we have an amine, typically a diamine right here, which has two or more amine functionalities. That amine acts as a nucleophile and ring opens that epoxy to give us our polymer chain. Okay, so typically our diamines here smell fairly bad, so that is the smelly component. And when it polymerizes, it does it such that we have a lot of places for it to hydrogen bond, and therefore it does not redissolve. And we typically have more than two functionalities of epoxy and more than two functionalities of amine, making it very, very insoluble and non-plastic. after it is done. All right, so that is our summary of the different types of step growth polymerizations. Our third section is going to be chain growth polymerization.